Hello, physics students. Before I jump into the topic for today, I first want to remind you the process that we took when we were studying electric field back at the start of the course. First, we began by studying point charges, dots of charge like protons and electrons. And we figured out forces, electric fields, and all those calculations, all algebra based. Then what we did is we moved on to distributed charge. What would happen if we had a bar of charge like this and we learned all the techniques for various shapes of finding the electric field? And generally the process went like this. We used the electric field formula kq over r squared for a single part of this, like a dot of charge if you were to slice it into a small little piece. And then we integrated to add up all the electric field vectors at a point. And we did that for various shapes. So direct integration of the electric field of each little part of the bar. And then in the third phase, we moved on to Gauss's law for finding electric field. So 3 big steps. At this point, we've completed the big step number 1 in our magnetism unit. We figured out how to find the magnetic field around an infinitely long wire, both in terms of the direction with this right-hand rule, and in terms of the magnitude with B equaling mu 0 I over 2 pi r. And then we figured out how to determine the direction of the magnetic force with magnitude and direction. Magnitude F equals QVB sine theta, and the direction with the other right-hand rule, this one. Okay, and it was a bit more complicated, but we completed our algebra-based treatment of magnetism. But all we know how to find the magnetic field of is a wire that's straight and infinite. But wires can be all kinds of shapes and lengths. So we're going to move on to figuring out the magnetic field of other shapes. And specifically today, a wire that's straight and a finite length. And later, we're going to find maybe a curved arc like this, a circular wire with current in it, or maybe a spiral of wire, finding the magnetic field in each of those instances. And what we're going to have to do, as you might suspect, like when we did distributed charge when we moved on, is we're going to have to integrate. But when it came to charge, we already knew the formula for the electric field of a single slice of a charge bar. It was kq over r squared. But when it comes to magnetism, we don't have such a formula for the magnetic field of a really tiny wire. We only have the formula for an infinite wire. So that is the topic today. We're going to learn an expression of the magnetic field caused by a little piece of wire. And then we're going to apply it to find the magnetic field of a wire that's straight and finite in length at the midpoint of the wire. So that's the goal for today. So the analog of E, electric field being kq over r squared, is the Biot-Savart Law, the topic for today. So here is the law, and this is a diagram, a graphical representation of the Biot-Savart Law, the patterns of the magnetic field around a little tiny bit of wire. And here's the mathematical expression saying the same information. So what is the pattern? If you have a little bit of current here, a little slice of wire, it creates magnetic field all around it. By this right-hand rule, thumb in the direction of the current, fingers in the direction of the swirl, we see that the magnetic field right above this little segment comes out of the board. Out here in front of the board, the magnetic field goes down toward the floor here. And then when I come around at the plane of the board again, it goes into the board. And then if I were to go inside this wall, it would be going up toward the top of the screen. So it goes around like this, as we studied with the infinite wire. But the Biot-Savart Law tells us more information, that the maximum magnetic field occurs at a 90-degree angle here. And as you go the same radius away at a different angle, the magnetic field gets smaller and smaller for these angles. And same here, as you deviate from a 90-degree angle to this ds, the magnetic field gets smaller, okay? Where did this come from? It's a law of nature. This is really how a little speck of current creates magnetic field around it. Written as a math expression, here it is. Mu 0 over 4 pi, the constants. I, the more current, the more magnetic field. That would make sense, right? And then the longer this little speck of wire is, the more magnetic field is created. That kind of makes sense. More wire, more magnetic field. And then this angular dependence in the sine theta formula. Notice that at 90 degrees, we'd have maximum magnetic effect. And at 0 degrees and at 180, there's no magnetic field. When there's current coming straight at you, you experience no magnetic field because of that current. And same when it goes away. And another dependence that's not shown here, divided by r squared. Further out, the magnetic field gets weaker. That would kind of make sense. When you're close, you have more magnetic effect. When you get further from this little speck of wire, it gets weaker. So there is the pattern. This is the analog of kq over r squared for a dot of charge, the electric field around it. This is for like a dot of current and the magnetic field around it. Once again, more complicated. With a dot of charge, it was just arrows pointing away. There was no angular dependence, and the direction was always away or toward, no right-hand rule, right? So I'll create a pause to allow you to copy this down. Now, let's apply it. Now, so for the next week, we're going to be applying this concept and this formula to various shapes, as I mentioned. And today, the straight wire segment of finite length, not infinite. What is the magnetic field around it? So let's move on. Example, a straight wire, finite length L. So we're going to find the magnetic field right at the midpoint of the wire. And so what we do is we proceed like with the electric field effect. We imagine a small slice of this wire of length dx, okay? So that's the length, and it's got a little bit of current because I didn't write it here. There is a current going through this wire like this, I, okay? Now, because of this, as we see over here, we're like, here's our ds, and we're like somewhere over here. So there's magnetic field that comes out of the board at this point, and the dimensions were a capital R away from the wire, and we're some distance x from the center of the wire. Then the magnetic field, dB, caused by that little dx with the current, is given by this expression. I just rewrote the Biot-Savart Law. Now let's fill in the pieces to this particular situation. So instead of ds, we're using x. ds is typically used for an arc. Then you have an arc length, okay? But when something's straight, we typically use x or y or even z, I suppose. So dx is the equivalent of ds. R is how far away this point is from that bit of current, which is like the hypotenuse of a right triangle right here. And we could find that from the square root of x squared plus r squared, or sorry, x squared plus r squared equals r squared. So that's what we have right here. The sine theta, I wrote it in blue here, so it kind of color coordinates. Maybe if you have colored ink, you could do that, so it'll be a little clearer on your notes. Or you could just draw an arrow down here like this. So theta is right here, and the sine of this right triangle will be opposite over hypotenuse. So the opposite side is capital R, and the hypotenuse is the square root of these two squared added together, so we get to the 1/2 power. So I filled in the pieces. Now what I'm going to do is just sort of touch this up a little bit, but before I do that, let me create a pause to give you a chance to copy this down. All right, so let's touch this up. Notice we could combine these two terms in the denominator. This is to like the 2 over 2, and this is to the 1 over 2, so they combine to the 3 over 2. And then all the constants on the top, I just, ran them across like that. There is my expression. Now, this is not the magnetic field of the whole bar. It's just the magnetic field of this piece right here, that expression up there. It's dB, not B. To get the total magnetic field, I have to sum up all the contributions of every piece of the bar. Now, and that's what we have right here. I'm going to integrate over the length of the bar. If the bar, first of all, so I took the constants out, put them all right here. This is all that's going to integrate the x terms. Furthermore, the limits. I'm going from this side to this side. Now, if the whole bar is L, but this is defined as 0, then this is going to be half the bar in the negative direction. This is going to be half the bar in the positive direction. So there are the limits. And when we did distributed charge, we needed another trig function here. Because remember that with distributed charge, when we're finding the electric field, if this bar were positive, for example, a bit of charge right here created an electric field like this. And then a bit of charge further over here creates an electric field like that. And these create electric fields this way. So the horizontal component canceled, only the vertical mattered. Nothing like that happens here. Every bit of this wire creates magnetic field coming straight out of the board. So they all align. It's not like they start turning like this as I'm integrating. They're all straight out of the board. And so no need to multiply by another sine or cosine here. We're just integrating this expression. Now, this is the expression, the integral that you can't really do by any kind of U substitution. Well, there is technically, but it takes a long time. So as I said when we're studying electric field, best to just memorize this one. And that'll be x over r squared times the term in parentheses to the 1/2 instead of to the 3 over 2. So that again, and for our limits. Now what remains is plugging in the limits and simplifying. So let's do that now. All right. Oh, yeah. Let me just erase this. Okay, so I don't think I created a pause yet, so let me create a pause in case you need a moment to catch up. All right, so let's plug in the limits. Let me just rewrite all the constants. Now notice we've got an r here and an r squared, so let me just get rid of that and have 4 pi r on the bottom here. And brackets. I plug in L over 2 for x. That gives me up here L over 2. And then x over here, plugging in L over 2, gives me L squared over 4. When I square L over 2, I get L squared over 4. To the 1/2 power. So I just plugged in L over 2 here and here. Now what I have to do is minus with negative L over 2 plugged in there and there, both places. So negative L over 2 on the top. And on the bottom, if I put negative L over 2 here and square it, the negative sign goes away and I just get L squared over 4 again inside this term right here. All right, well, this minus and minus basically turn into just plus. So I've got L over 2 plus L over 2 in the top, which just gives me L, because I already have a common denominator here. So this just becomes mu 0 I L over 4 pi Okay. Now, technically, we could just leave it here and be done. But for whatever reason, I see this done a lot where they just do this. They say, okay, let's just make this 2 over here and then 2. So we got 2 times 2, which is like the same as 4. And that will allow us to bring this 2 under the radical. And when you bring something into a square root, into a radical, you have to bring it in as the quantity squared. So what I'm going to do is by bringing this inside, I'm really bringing it in as a 4 to put in the radical. So then this just simplifies to oops, I lost the R over here. So I squeezed it in there. Sorry, it looks a little messy, but and so that last thing I just did was just a quick way or a way to get rid of this fraction within a fraction, make it look a little nicer. So let me create a pause to allow you to catch up if you need it. Okay, so a common theme that I'm going to be doing throughout this, the rest of this topic, magnetism, is a unit check. Remember with electric field, I always said, well, compare it to kq over r squared and see if the units check out, because sometimes it will allow you to catch a mistake. So we can do a unit check by comparing this formula to mu 0 I over 2 pi r, the basic formula for the magnetic field around an infinitely long wire. That means you have to have a mu 0 times an amps over a meter, the units when I plug in the various quantities here. So I've got my mu 0 here, and then I've got amps for current. Okay, good. But then I have a meter on the top. Okay. And then on the bottom, what do I have for units? Well, I've got this meter, and then this is meters squared, square root, which basically gives me a unit of a meter, this whole term right here. And what I could see is that what I have is mu 0 amps over meters, like what I'm supposed to have. Remember, I lost this R, but I caught it. But if I didn't catch it, I would have had mu 0 amps, and then all the meters would have canceled. I said, oh, mistake. And I could have gone back and maybe found this. Oh, okay, now I know that that's missing. If I lost the pi, for example, wouldn't help me. But variables missing, certainly you can find those by unit check. All right, so there's the formula. A couple more things that I want to do is now use this to determine the magnetic field of an infinite wire. Well, we already know that, right? We just wrote that down as an expression earlier in this magnetism topic, mu 0 I over 2 pi r. But that was just like an expression pulled out of the air, okay? And so what we're going to see is where it comes from, because it comes from this formula. How so? Well, if we wanted the magnetic field of an infinite wire instead of a finite wire, we'd take this formula and we would find the limit as the length of the length goes to infinity of this formula. All right, so we need to look at this formula, see what it approaches, what value, what function, as this length gets longer and longer. To help us do that, what I'm going to do is multiply top and bottom by 1 over L. And so that eliminates the L on the numerator, and leaves just mu 0 I. L divided by L. And then in the bottom, what I'm going to do is bring this L under the radical, which comes in as 1 over L squared. Not 1 over L, but 1 over L squared. So that's going to be L squared divided by L squared 1. Plus this term divided by L squared. And now if I look at this formula, I could see that as L goes to infinity, this term over here is going to go to 0 because I'm going to be divided by infinity. So I'm going to have the square root of 1. That's what this term will become. In other words, just 1. And so the magnetic field is mu 0 I over 2 pi r for an infinitely long wire. So let me give you a moment to copy that down. All right, so that formula didn't just come out of the air. I wrote it out like that, and oh, here it is. No, it comes from the Biot-Savart Law. So the Biot-Savart Law is like the root of magnetism, finding the magnetic field around a wire. You could use it to find the magnetic field of any shape wire, an infinite one, a short one, a curved one that spirals, a circular wire. Any shape, if you use the Biot-Savart Law, it will give you the magnetic field, okay? So it's like the heart of magnetic field. So that's example 1. I just want to point out a couple quick examples before I finish for today. You could also find, I think it might even be a homework problem, we found the magnetic field here in the middle. And that meant the limits were minus L over 2 to L over 2. But you could find the magnetic field here pretty easily. It's the same analysis as we just did. The only difference is that the limits would be from 0 to L in our integration. Or you could even find the magnetic field possibly here. And then the limits would be minus L to 0. You'd get the same answer, okay? And you could look at your integral and see that that would be the case. So very easy to find the magnetic field anywhere along here by just changing the limits. Like maybe here you could say minus L over 4 to 3/4 L. So not bad, okay? Just give you a different kind of looking formula. And one other, let's see, what color have I not done yet? Right here or here. You don't even need to do any analysis at all. You would just know right away B equals 0 when the current's coming towards a point or away from a point because of the nature of the Biot-Savart Law. So that's the topic for today. I don't have it here. I erased it, the Biot-Savart Law. Look back at the beginning of your notes, the picture pattern of showing the most magnetic field here and here around a ds, and then weaker as you go away from the 90-degree angle. And that's why there's sine theta in the Biot-Savart Law formula. And then weaker as you get further from this little wire segment. That's why there's an R divided by R squared. That's the pattern of how magnetic field is created by a little speck of wire. And then look over the main points of the integral, in this case, to find of a segment. Okay, so I hope you enjoyed. I'll see you in the next couple videos where we find the magnetic field for other shapes, arcs and spirals and whatnot. So I'll see you in the next Biot-Savart Law physics video.